Welcome to my channel called Aeropib, and today I'm going to do a technical review of version 13.3. It's called version 13 because this is my 13th attempt at building a flying object, and 0.3 because this is the third iteration. Now, my purpose is to build a highly efficient multi-copter system for drone delivery and also drone imaging of the environment, or mapping, for instance. And to do so, I've chosen to build a rocket-shaped slender vehicle that has 2 motors rather than the traditional 4. Now, my preliminary calculations have shown that in this configuration, 2 motors with 2 large rotors will be more efficient than 4 small ones in a quadcopter. The structure of V13.3 is modular, and it is composed of 3D printed material called PLA, which stands for polylactic acid. Now, it's very important in my case that this vehicle be modular, because if one module breaks, I don't have to replace the entire vehicle. I can just replace that one module. If one of these legs break, I don't have to replace the entire vehicle. I can simply print a new leg. So when you go about building this, keep that in mind. Now onto the electronics. So I'm powering this vehicle using a 12.6 volt lithium polymer battery, and that power then goes through a speed controller. The speed controller regulates the amount of power that goes to the motor. Now, I'm using 2 motors here, and they're both counter-rotating in order to cancel out any torque effects. Furthermore, I use 2 servo motors in order to control the roll and pitch axes, and I use a radio transmitter as well as a radio receiver to send signals to tell the drone where to go, how fast to go there. For the flight control system, I specifically use a KK2 board. However, you can also use a PX4 board, or really any board you'd like, as long as it's able to keep the drone stable and has some sort of control system on board. Now, I soldered these electronics, and I also used heat shrink wiring as well, heat shrink tubing, and put them on the wires. So here's the roll and pitch axes I talked about earlier. And those roll and pitch axes are controlled by the 2 servos. Now, I also use a ball and socket joint, which can't exactly be seen here, but that's what the 2 motors are sitting on top of. A ball and socket joint, similar to the one in your hip. And all that does is provides movement in both pitch and roll for the vehicle. And then I call yaw control the side-to-side movement about the vehicle's own cylindrical axis. I call that yaw control, and that is controlled by differentiating the thrust between the motors. So if I want to turn one direction, I turn one motor's thrust higher than the other, so that it spins faster than the other, so I get a torque, allowing me to do yaw control. And in general, that is the technical overview of the most important aspects I've learned of this vehicle so far in creating it. Now, I can go further into each of these systems in the future if you're interested. For instance, I'm currently building my own control system from scratch as an exercise, and I'm also implementing the PX4 control system in order to add GPS capabilities to the drone. When it comes to the electronics, I can talk further on these LED lights here. For instance, these LED lights are controlled by a microcontroller, and I find LED lights very important, not just for the aesthetics, but more importantly, so that the drone can communicate with me. So, for instance, if I code the motors to shut off, the servo motors to shut off, the camera to shut off at a certain time, and then after that happens, I code the lights to turn green, signifying that the drone is saved, then I can know that it's all right to approach it. So that's one way I can communicate with the drone physically, so I can see exactly where in the code the drone is at. In addition, I could talk more specifically when it comes to 3D printing, which printers to get, which printers to use in my experience, and also when it comes to the construction of the legs here. And so these legs may change. Right now I'm performing finite element analysis studies on them, and it's critical because these legs have to take an impact, especially when landing in perhaps unknown conditions. And these legs will have some sort of impulse response that will then be transmitted to the body. So when modeling that in a finite element analysis program, it's critical to use a beam and shell model and do some sort of dynamic simulation, because a static simulation won't account for the additional loads on the vehicle due to the impact. So those are additional topics I can talk about with respect to the structure, electronics, and control system. And if you have any more questions, please leave them in the comment section, and I'll love to answer them or make a video about it. So thanks for watching.